Well, welcome everybody back to the afternoon session. Our first speaker is Miloslav Štěpán, and he is at Masaryk University working with John Borg and will tell us about quasi-limits and lax flexibility. Take it away.
Yeah, thank you very much. Thank you for this opportunity to talk or speak at this seminar or conference rather. Okay, so what this will be about first, I will basically be talking about some two-category theory and to be more specific, some two-dimensional monad theory and some lax versions of some pseudo concepts basically. So first, I will recall some definitions in two-category theory. Then I will recall results in two-dimensional monad theory. And then I will talk about lax versions, as I said. And in this talk, I will basically answer two kinds of questions. One of them is what kind of colimits do two categories of lax structures admit? And the other question is how to capture or how to describe multi-categories as co-algebras. Okay, so some two-category theory. Yeah, so here I recall the notion of a two-monad. So the definition is as for ordinary monad, except it's two functors, and the multiplication and the unit are two natural, but the equations are the same. In two-category theory, if you have a two-monad, you can consider various degrees of strictness for algebras for two-monad. So, for example, a lax-T algebra consists of an object, a morphism like this, from PA to A, together with this two-cell associator and uniter. And these are subject to some higher associativity and unit laws. If this gamma and iota are invertible, it's called a pseudo-algebra. And if there are identities, it's called a strict algebra. Okay, I will introduce some key players for this talk. One of them is the free strict monoidal category two monad. So it's given by this equation or this description. And strict T algebra is precisely a strict monoidal category. So when the tensor is strictly associative. And pseudo algebras are equivalent to ordinary monoidal categories. The other key player is the small presheaf pseudomonad. Now, this is actually, this presentation is a pseudomonad, but that's a detail that won't be important. But okay, so how is this presheaf pseudomonad defined? It sends a locally small category to a full subcategory of the presheaf category consisting of small presheafs. And what's a small presheaf? Presheaf is said to be small if it's a small colimit of representable. Now the unit of this pseudomonad is given by the Yoneda embedding. Yeah, I will not talk about the multiplication. But what's important is that a pseudo algebra for this pseudomonad is a cocomplete category. Okay, let me recall the notion of morphisms between algebras. So again, there's various degrees of strictness. So a lax morphism between algebras A and B consists of this one-cell component together with a two-cell component that are again subject to some laws. If F bar is invertible, it's called a pseudomorphism. And if F bar is the identity, it's called a strict morphism. Examples include monoidal functors, pseudomorphism for the free strict monoidal category two monad. The other example I have here, so you can consider two meet semilattices with the greatest elements. You can regard them as strict monoidal categories, and then any order preserving map is automatically lax monoidal. So this is, yeah, right. There doesn't have to be an equality, but inequality. And pseudomorphisms for the presheaf pseudomonad is a co-continuous functor. So that, yeah, and yeah, there's various two categories you can consider. So, and that will be relevant in this talk. So I denote by T-alg as the two category of strict algebras and strict morphisms. And then based on what's in this bottom right index, you can either consider strict morphisms or pseudomorphisms. Well, it's denoted by nothing here, or lax morphisms. or you can consider pseudo algebras, denoted like this. And we've got these inclusions, and the natural question would be to ask, when do they have adjoints, which is what I will do. But before that, let me recall one last thing, which is the notion of a lax-idempotent two-monad. So a two-monad is said to be lax-idempotent if the multiplication is a left adjoint to the unit. Yeah, and in case this adjunction is actually an adjoint equivalence, this is called a pseudo-idempotent two-monad. These lax-idempotent two-monads have this particular property that an object admits a structure of a pseudo-algebra if and only if the unit evaluated at that object admits a left adjoint. So that's so like the structure of a pseudo-algebra on an object is essentially unique. It's unique up to isomorphism. And examples include the small presheaf pseudomonad. I've told you that one is lax-idempotent. And if you want an example of a pseudo-idempotent one, there's the Cauchy completion two-monad. And I haven't described it here. Yeah, but it's given sending a category to its completion under absolute limits, colimits. Okay, so yeah, now we are getting to the two-dimensional monad theory. So let me recall some known facts. For example, this one. So if T is a two-monad, and if your two-category of strict algebras and strict morphisms admits a certain kind of colimits, then the inclusion of strict morphisms into pseudomorphisms admits a left adjoint. Let me denote the unit of this adjunction by P, which is a pseudomorphism. Let me denote the co-unit by Q, which is a strict morphism. Now, as any adjunction, this adjunction generates a two-comonad on the two-category of strict algebras and strict morphisms, and I will call it a pseudomorphism classifier two-comonad. It's a long name, but it's denoted like this Q and small p there. Yeah, by the way, the same story holds for lax morphisms. So I have repeated it here. Again, if the two-category of strict algebras and strict morphisms admits some colimits, then the inclusion of strict morphisms into lax morphisms has a left adjoint, and it generates a comonad that I denote QL and call it the lax morphism classifier two-comonad. Now in the paper Two-Dimensional Monad Theory from the 90s, they've actually proved these things under some slightly different assumptions. The formulations I'm using here come from the paper Codescent Objects and Coherence from 2002. And yeah, but in this paper Two-Dimensional Monad Theory, they proved the following. If your two-category or your base two-category admits pseudo-limits of arrows, then for every algebra, you actually have that the unit and the co-unit of the adjunction I've told you form an adjoint equivalence, such that so the co-unit is the retraction for the unit. In particular, this means that the pseudomorphism classifier comonad, this QP, is pseudo-idempotent, which is quite a rare property, I would say. And in the lax case, the same thing holds, or similar thing. If your base two-category has lax limits of arrows, the resulting two-comonad is co-lax-idempotent in this case. Another important theorem in this paper I'm mentioning was that you can turn, so I nickname it a big bi-adjunction theorem. And the point is, if we have an adjunction like this, it induces such that the right adjoint factorizes through pseudomorphisms, it induces a bi-adjunction like this between pseudomorphisms and some two-category L. Now, one interesting corollary of this theorem is the following, that if your strict algebras and strict morphisms, if that two-category is cocomplete, then strict algebras and strict morphisms is bicocomplete. And I was interested what happens in the lax version. So the question would be, is strict algebras and lax morphisms bicocomplete under some conditions? And the answer is no. You can consider, for example, the two categories of strict monoidal categories and lax monoidal functors. And it's not bicocomplete because it doesn't have bi initial objects even. And it's not difficult to prove. Okay, so I've told you the classical story. Now here are some lax versions. So the question is how to properly generalize the results from two-dimensional monad theory. And the first step or first thing I noticed is that the theorem of this thing actually holds in more generality, and it holds like this: if Q is a pseudo-idempotent comonad such that the base to category is cocomplete, then the Kleisli to category is bicocomplete. Yeah, and it admits a quite formal proof. And yeah, and so why does this specialize to pseudomorphisms? In case the two comonad Q is the pseudomorphism comonad, you obtain the result that T alg is bicocomplete because T alg is the Kleisli two category for the pseudomorphism classifier comonad. So this was this observation, but yeah, pseudo-idempotent two comonads are quite rare. So now this step into lax world meant that I wondered what happens if I replace pseudo-idempotent comonad by a colex idempotent one. Now, as I told you, now in this case, the Kleisli two category won't be bicocomplete, but it will be something weaker. So I had to define an appropriate lax version of bicolimits. Yeah, so let's recall the notion of bicolimit first now. So if f is a two-functor, we say that a cocone is a bicolimit of f if this canonical transformation or this canonical functor that sends some morphism, one cell, into this whisker with the cocone, if this is an equivalence. Now, if this is an isomorphism, then it's ordinary colimit, right? If it's an equivalence, then it's a bicolimit. And you may wonder what happens if we only require that it's a left or right adjoint. And what happens, you get the notion of a quasi-colimit. So the quasi-colimit were defined already in the 70s in the paper Formal Category Theory Adjointness for two categories. But since then, I do not think, as far as I know, I don't think they have been studied really much. The notion is a little strange, but I guess it's still not that crazy. It's a particular example of a weak enriched colimit that has been studied by Rosicki and Leck, for example. I will focus on one quite special case of quasi-colimit in this talk, which is the following. So let me propose the definition. So if you have a two category and a two functor, we say that this cocone is a Rayleigh colimit of f if this functor is a Rayleigh. And what does it mean? It's a shortcut for right adjoint, left inverse. So this means that this functor, I require it to have a left adjoint such that the counit is the identity. And I have written down what does it in particular mean. So we have this cocone, and we say that it's a Rayleigh colimit cocone if for every other cocone there exists a map like this. So this is in particular a weak colimit, like in the classical one category theory sense, where we get this comparison, but it doesn't have to be unique. So that's the kind of one-dimensional aspect of it. And the two-dimensional says roughly that, says the following. So if you have a one cell, and any one cell whatsoever from C to A, and a modification from gamma to this colimit cocone composed by this theta. So I will tell you what's a modification. Then there exists a unique cell sigma bar. So what's a modification in this case? Modification is a collection of these two cells that satisfy some equations. And I require that there exists a unique two cell such that if I precompose it with the length of the colimit cocon, then it's equal. Okay, one example that's quite easy is actually the following. So we may wonder what happens if we take the we take initial objects. So an object is Rally initial. So for initial objects, the category of cones or cocoons actually is terminal. So there will be just a star here or the point. And now the object is Rally initial if for every A, this object, this unique functor into the terminal category has left adjoint. But this happens if and only if this home has an initial object for every, sorry, this is supposed to say I, or sorry, A, not I. So so like Rally initial in this case means the homes have initial objects. And okay, I have one example that's, I guess, quite natural. So you can consider the two categories of strict monoidal categories and lax monoidal functors. And now I claim that the terminal monoidal category is actually Rally initial. It's definitely not an initial object or even by initial, but it's Rally initial because for every strict monoidal category, we have following isomorphism. So the home from the terminal into A, if you take lax monoidal functors, it's actually isomorphic to the category of monoids in a monoidal category. And for every monoidal category, this category on the right side has an initial object that's given by this monoidal unit. Okay, I have written down explicitly so you can get some more intuition, I guess, what happens for Rally coproducts. So again, it's like this cospan, such that for every other cospan we get this comparison map that doesn't have to be unique, but such that these two commute. And yeah, now the two-dimensional aspect says that if you have two cells like this, there exists some unique two cell that goes from the comparison map. Yeah, so it's kind of strange maybe. And these Rally colimits, they sometimes have appeared here and there, I guess. But okay, so one thing what I've proven about them. So yeah, remember the big bi-adjunction theorem? It was this one. It says that if you have this adjunction, it reduces or it induces this bi-adjunction. So the similar thing holds if you take lax morphisms here, and then you had a lax adjunction here. And now what's a lax adjunction? You know the notion of an adjunction. It's an isomorphism of home categories. Then you have bi-adjunction, which is equivalence of home categories. And now lax adjunction induces an adjunction between home categories. So it's kind of very weak. But what's important that this theorem has the following corollary. So if Q is a lax-idempotent 2 comonad that's on a two category that's 2 cocomplete, then the Kleisli 2 category is Rally cocomplete. So it has this kind of weak colimits. Now the proof of this fact is quite formal, and I guess the advantage of that is that admits 4 kinds of duals. Actually, you can consider lax or lax-idempotent and monads or comonads. So one version of it is the following: that if you have lax-idempotent 2 monad, which are definitely, I guess, more prevalent there than comonads, maybe, I don't know, then the Kleisli 2 category is Rally complete. Now, if I switch monads for comonads, I have complete here. So in particular, if I take my 2 comonad to be the lax morphism classifier comonad, this gives me that the 2 category of strict algebras and lax morphisms is Rally cocomplete. You know, about this 2 category of strict algebras and lax morphisms, there are papers on about limits in this 2 category, but I guess not so much has been done about the colimits, and for a good reason, because there are not like strong colimits, or usual, but I guess there are these weak ones. So an example, a concrete one, is the strict monoidal categories and lax monoidal functors. Okay, now if we use the power of the dual version, let's consider the pre-shift pseudomonad again. Now a Kleisli morphism. So let's determine what's a Kleisli two category or Kleisli bicategory for this pseudomonad. A Kleisli morphism is a functor from A to PB, and the PB it's like subcategory of pre-sheaf. Now it transposes into a profunctor, which I call small, which means that if you fix this A, then the result is a small functor. And in fact, the Kleisli bicategory is bi-equivalent to the bicategory Prof of locally small categories and small profunctors. And from the results, it seems that, it seems to be the case that Prof admits all Rayleigh limits. So these weak limits are in Prof. Okay, so I'm quite fast. So this was, I guess, one thing that I studied a lax analog of, this lax version of bilimit. The other thing is flexibility. So let me recall again this adjunction we have seen between strict morphisms and pseudomorphisms, and the two commonad QP. I will use it a lot. So, and in the classical paper, T algebra is defined to be flexible if the counit of the above adjunction, which is this strict morphism Q, is a retract equivalence in strict morphisms. Now, it's always a retract equivalence in pseudomorphisms. This follows from what I've shown you, well, at least under the assumption that the base admits pseudo-limits of arrows. But if we require its retract equivalence in strict morphisms, then we call the algebra flexible. And there's a similar notion of a semi-flexible algebra, and we define it if QA is an equivalence in strict morphisms. Now, these flexible algebras are actually quite interesting, I would say. They have some interesting properties. For instance, if you have a semi-flexible algebra, then every pseudomorphism is isomorphic to a strict one. And for example, the place where these appear, there's a good notion of model structure on strict algebras, and these flexible algebras are the cofibrant objects for this model structure. Okay, and there's following proposition that actually, I guess, appeared in the paper of Borg and Garner, which says that T algebra is semi-flexible if and only if it has the structure of a QP coalgebra, sorry, pseudo QP coalgebra. And algebra is flexible if and only if it has the structure of a normal pseudo QP coalgebra. By normal pseudo algebra, I mean that the uniter to cell is the identity. Yeah, so this proposition tells us there's a connection between flexible algebras and these QP coalgebras. Yeah, so and this prompted Borg and Garner to define call a T algebra pi if it has the structure of a strict QP coalgebra. And I have some examples that are known. For example, if you consider weights, so two functors from some two category to cat, or one category, I think, I'm not sure. So W is a pi algebra for the pre-shift two monad on this cat to the power of objects of J. So the following are equivalent. So it's pi algebra if and only if it determines a pi limit. So a limit built out of product, inserters, and equifiers. And the third equivalent condition is that the composite, if you post-compose it with the functor that sends a category into its set of objects, then this is a coproduct of representables. In other words, a free pre-sheaf. In that paper I mentioned, they also give examples of pi monoidal categories. So a strict monoidal category is pi if and only if the underlying monoid on objects is free. So in this case, being pi means this, the structure on objects is somehow free. the underlying structure on objects is free. So now, so I've told you how you can replace the pseudomorphism classifier comonad by a general two comonad. That's, I guess, pseudo-idempotent or quasi-idempotent. Now, if you do it here, if you replace QP by a general quasi-idempotent comonad, now the study of semi-flexible, flexible, and pi algebras becomes the study of just Q coalgebras. And yeah, for the remainder of the talk, I will focus on what happens if we focus on the lax morphism classifier two comonad. You know, that's the one that's induced by the inclusion and a reflection to the lax morphisms. And I propose the following definition. So we will call T algebra lax pi if it has the structure of strict QL coalgebra. So, and this, I'm not sure where they, well, lax pi weights have been considered somewhere at some point, I think, but I'm not sure if I've seen it. Yeah, but we can talk about later. So yeah, before I continue, I have to tell you a bit about ket T. So if you have a Cartesian monad, which is monad that preserves pullbacks, and the multiplication and unit are natural transformations, now this gives a rise to monad ket T that's defined on the two category of internal categories, and it's given by this. Is defined pointwise basically. An example is if you have a free monoid monad on sets, ket T is the free strict monoidal category to monad on ket. Now, yeah, there is this theorem that was already mentioned today, at least its specific form. So there is this adjunction. Yeah, if you have a Cartesian monad, you can consider T multi-categories, which are generalized multi-categories. I do not have time to delve into details, but the point is you can consider an adjunction between T multi-categories and strict algebras. So there's an adjunction like this. And actually this adjunction generates the lax morphism classifier comonad on strict algebras. Yeah, now you can prove actually that this functor U or two functor is comonadic. From which it follows that T multi-categories are equivalent to QL coalgebras. So yeah, so essentially if you have a two monad that comes from a Cartesian monad on sets, for example, then lax pi, the algebras are T multi-categories. Now, how does this work? If you go from the left side to the right side, you just send a multi-category to the free algebra on it. For example, you send a multi-category to a free monoidal category on it. But the other direction is, I guess, more interesting because there, if you have an algebra that has a QL coalgebra structure, it somehow has encoded in it certain prime elements, and those prime elements generate the multi-category. But yeah, I do not have time, but I can give you some examples. For example, monoidal category is lax pi, if and only if there is some underlying multi-category such that A is a free monoidal category on M. And actually there's so you can do the same for two monad whose algebras are double categories, and a double category is lax pi if and only if it's there is an underlying virtual double category such that X is free double category associated to D. So this is a special case of what Dawson, Paré, and Pronk have been studying in the paper, paths in double categories. Another example is two functor is lax pi if and only if there is some other functor over J such that this functor W is actually given by sending B to this comma category. So in this case, it's quite restrictive, but this, for example, includes weights for lax-limit. So I guess, so the ordinary pi algebras mean that there is some free structure on the underlying objects, but the lax pi one tells you that there's some underlying multi-category in your algebra. Yeah, there's some things I haven't said. For example, some characterization of semi-flexible algebras that have been studied in these papers. actually they can be generalized to give characterization of Q coalgebras for a general lax-idempotent to monad. So you can give, and this dualizes, so you can give some characterization of P algebras, for example, some characterizations of algebras for the pseudo-idempotent, lax-idempotent pseudomonad P. And now, one further, I guess, thing I'm interested in is that, so QL coalgebras for this special kind of two monads are multi-categories. So I would be interested what happens to some more general kind of two monads. So whether it's some kind of generalized multi-categories or what is it? Now there's some references. So in this paper on familiar to functors, preservation of comma objects as Rayleigh colimit has appeared here. And I've mentioned the other ones. Okay, so thank you very much.
Thank you, Miloslav, and let's thank our speaker with a virtual reaction. Are there questions, comments? Simon?
Yes, regarding this last question you asked at the end about, or like direction of research about, what does it give for something that doesn't come from a Cartesian monad? What are the QL coalgebra? Have you looked at any single example of something that's not a Cartesian monad, just to give us an idea of the sort of thing we can get?
So something that doesn't come from a Cartesian monad. I'm not sure if I've looked at any ones that are not of this form.
Okay.
So I haven't looked at them yet, but
okay.
I want to definitely.
Well, thank you.